So as you can see now, I have a much simplified circuit for multiplication. I no longer need to shift my multiplicand. My multiplier now is initialized in the lower half of my product register, and I'll be shifting my product register to the right. And one of the greatest advantage of this circuit is that I no longer need the 8-bit adder. I can have a 4-bit adder. And if you recall from the lecture on addition, remember that one of the main problems to make an adder faster was the problem of the carry look ahead, or the carry ripple effect, that it took a long time for the carry to propagate from the initial carry in to the final bit of the adder. By having a smaller adder, I am already accelerating my multiplier significantly. So let's see how this multiplier is going to work. So again, the initialization was the multiplicand goes to the multiplicand register, the multiplier goes to the multiplier register, and my control unit now will be checking the least significant bit of the multiplier to see whether I need to be adding the value of the multiplicand to the product. So let's see how this is going to work. So my control unit first check, and my initial bit in the multiplier is 1. So it's going to tell the adder to add the value of the multiplicand to the product, but it's only adding the upper part of the product. So by doing this addition, that bit that's marked there becomes 1. And then the next thing that the control unit does is simply to tell the product to shift to the right by 1. And then it checks the lowest significant bit again. It's a 0, so it's going to tell the adder to not add this time. And we'll tell the multiplier to shift to the right again. Again, the bit is 0. There is nothing to do other than simply shifting to the right again. And now I have a bit equal 1. So I now will add the value of the multiplicand to the upper bits of the product, so that I get that 1. And finally, I do my final shift, and that is where I get now my product. That's the product that I expected to get. Here we kept it in the slide to make sure that we are getting the correct result. So this is a much more efficient hardware for multiplication than the initial one that we produce, because it has a smaller adder. And this is the final product after I did the K-shifts. But that multiplication is still not fast enough. Maybe I could have a faster multiplication. What I do is to actually compute now all the partial products that in that previous example I didn't. I just kept accumulating to the same. So now what I'm going to do, I'm going to compute each one of the partial products, and I'm going to store those partial products in 8 bits. So the idea here is that I'm going to be trading off storage for speed. I want my multiplication to be faster. So if I take each one of the bits of the multiplier and I multiply by the multiplicand by shifting it. So the initial bit I use just the multiplicand. I get 0, 0, 0, 1, 0, 0. The second bit I do it by shifting by 1. I multiply by 0, so it's all 0. The third one I shifted by 2. And in the last bit, I shifted the multiplicand by 3, and I obtained this result. So now I have all the partial products computed, and what I'm going to do is I'm going to add the value of those two partial products together, because what takes the most time in the multiplication is the addition. The shifts and the multiplication by a single bit is simply a copy of values. It takes much less time than the addition, which takes more time. So I have now added those two partial products, and now I can add those two partial products to obtain the result in here. So this will be a faster multiplication because these two additions can be done in parallel because they are adding different numbers. So in a faster multiplier, I have many more adders because I need to do my additions in parallel. So this is a cost performance trade-off. My faster multiplier will be more expensive because it's going to have many adders, but I'm going to be able to perform. So if you take the longest path from the top to the bottom of the tree here, what you're going to notice is that the longest path is the logarithm of the depth of the number of elements in the tree, which would be a much faster way to do the multiplication. Now, this is not fast enough for me. I wanted to do it faster, and to do it faster, I'm going to use a technique called pipelining. For pipelining, what I'm going to do is the same thing that you are already used to see in assembly lines. And here there is an example from the textbook that is using a laundry example. We're going to revisit this example later in November, but let's take a quick look at this example. Let's say that washing takes 30 minutes, drying takes 40 minutes, folding takes 20 minutes. If you were to do wash one load of laundry, then dry, and then fold, before you start the second load, it will take you this long for you to do the 4 loads. However, if you were to, instead of doing that, you were to overlap the drying with the washing and then with the folding, you can finish the entire task in much shorter time. And maybe you have still time to study for the midterm after that. So that is the idea of pipelining. Another idea of pipelining, one of the students from 229 that built this slide found this video illustrating what is pipeline. I want you to watch the video and pay attention to what's going on at the bottom of the video here. And so to do that from the beginning again, now that you had fun seeing the video once, I want you, let me go back to that slide and play that again. And now that I play that, you see what's going on with the assembly line. I want you to pay attention to what's going on down here. This is each one of the stations in your pipeline, or each one of the stages in your pipeline. Or you can think about stations in your assembly line and see what's happening. And this is time. Over time, what happens? As I play, I need to go back. I wanted to play this video again here. So as you can see, the first time only the first unit is busy. The second time I have 2 units busy, then 3 units busy, and finally the pipeline is full. Then every time, every one of the units is busy, and I'm producing a full mask in each cycle. In the end, when I finishing the pipeline, I will slowly making these units idle, because I'm done with my job. So that's the idea of pipeline. And what we're going to do is use the idea of pipelining in our matrix multiplication. So again, I'm doing the same operation as we have been doing this slide, but now I have other multiplications to do. So the idea here is that I don't want to do only one multiplication operation. My task is to do many multiplications. So sorry for the people that may be colorblind, but the first multiplication here is the red one, and is multiplying these 2 numbers that we have been multiplying so far. The one in the middle is my blue one, and you can check that the numbers are different. And the one on the right is my green one. So what I'm going to do is, in the very beginning of my process, I'm going to compute the partial products for my red multiplication, and I'll put them on the top of my adders. Then, in the next clock cycle, I'm going to compute the addition at this level, and at the same time, I'm going to be computing my partial products for my blue one, the one in the middle, and I'm going to put the input of my adders. In the next clock cycle, I'll be computing the addition for the red one down here in this adder, and These adders will be computing the partial additions for the blue, while the green one comes to the top of this adders tree. So by creating the adders tree, I made a single multiplication faster because I can do my addition of the partial products in parallel at any level of the tree. And now by pipelining it, I can execute multiple multiplication operations at the same time, as long as each one of them is in a different stage on my pipeline through the tree. This is much closer to how multiplication is actually implemented in the hardware. Pretty much all processors today that have multipliers will have some kind of pipeline in the multiplier to one, optimize resources, and the other to make it faster. In RISC-V, we have 4 instructions to produce a properly signed or unsigned 64-bit product. So there is a mul instruction, MUL. It takes two 32-bit source registers and produce the lower 32 bits of the products in the destination registers. So if the higher bits of the product in this instruction would be lost. And then I have also mul age. That is an instruction that will also perform the 32 by 32 bit multiplication, but will place the upper 32 bits of the product in RD. So if I combine an MUL with a MUL age instruction, I can then obtain all the 64 bits product. So I also have a mul age U instruction that will do the 32-bit by 32-bit multiplication and place the upper 32 bits of the product in RD. And a mul SU instruction will also perform the 32 by 32 bit multiplication. This is signed versus, the mul age U, both operands were unsigned. The mul age SU, the first one is signed, the second is unsigned, and I will put the upper 32 bits of the product into RD. So for a 64-bit multiplication where I want the 64-bit from the 32-bit, I would be doing a sequence of operations, such as I will put 2 operations in sequence in my assembly code. It's advisable that those 2 operations appear exactly next to each other, because what will gonna happen is that the microarchitecture, that is the internal architecture of your RISC-V processor, will see those 2 operations being fetched one next to the other, and will merge both of them into a single multiplication operation. So it's not like you are doing the multiplication twice, you are doing the multiplication just one time, but you are specifying what are the registers where you want the result to be. The microarchitecture takes care of doing the merge for you. There is hardware for division too. Your textbook has a discussion on how to do division by hardware. We're not going to discuss how we do division by hardware here. You can use the same hardware that is used for multiplication can be used to do division. Let's just discuss what happens with the division in RISC-V. We have 2 instructions for integer division and 2 instructions for the remainder. We actually, in our in-class exercise, we already use the remainder instructions when we computed the greatest common divisor. And so we have instructions for division that both handle signed and unsigned integers. So the first one is the division, and it can be signed or unsigned, and then you have the remainder instruction that also you can compute the remainder for signed or unsigned numbers. The RISC-V divide instruction will ignore overflow and will ignore division by 0. the software has to check to see if the operand, the divider is 0 before performing division instruction. The hardware will not gonna alert you that you are making a division by 0.